Hi guys, welcome to the practice problem video for the fluids and electrolytes exercises. I think it's fairly important to sort of understand what's going on when you give a patient fluids or when a patient loses fluids. And one good way to thoroughly understand that is to do problems like the self-study problem that I'm about to do now. These are at the end of my lecture notes. Now bear in mind, nobody expects you as a real clinician to go through and fill out a chart like this. That would be ridiculous. But for right now, as students, somewhere in the back of your mind, you have to recognize what's going on when fluid imbalances take place. And so in order to do that, working through these problems in a quantitative way can really help give you a feel for how water distributes throughout the body during disease or during treatment. Okay, so problem number one: a normal 60-kilogram man of average build, meaning not too fat, not too thin. If you're too fat, then your percent body water is as a percentage of your body water as a percentage of your body weight is less than normal. So this guy's normal. He quickly drinks 2 liters of tap water, and his osmolar and fluid compartment sizes are normal. We're going to call normal 300 milliosmoles per liter. And what you need to do is calculate the size of the compartments, extracellular and intracellular, and the osmolarity of the compartments calculate before and after he drank, okay? And to do that, we typically use this chart. So this chart has total body water, extracellular fluid, intracellular fluid on it, okay? And it has the volume of each compartment, the quantity, that means milliosmoles of particles in each compartment, and the concentration, milliosmoles per liter in each compartment. We're going to fill this out based upon the information that we got here. So start means before the guy drank anything, okay? So this guy is 60 kilograms. He's got average build. And so we want to know what the volume of his total body water is. Well, as a male, we use 60% of the body weight as the weight of body water. And of course, 1 kilogram is equal to 1 liter. So the first thing we're going to do is calculate the total body water. And that is 60% of this guy's body weight. Now remember, we use 50% for ladies, 60% for men. This is a man. So total body water is equal to 60 kilograms, which is his weight, times 0.6, and that equals 36 kilograms of water, which is 36 liters. So we start with 36 liters of water of total body water, okay? So how much of that is extracellular and how much of it is intracellular? Well, we know that the extracellular fluid is 40% of the total, and the intracellular fluid is 60%. So extracellular fluid equals 36 times the total body weight, which is times 0.4, and that equals 14.4 liters. And the intracellular fluid is the other 60%, and that is equal to 21.6 liters. Okay? So here we have 14.4. Whoops, let's go ahead and do that. 14.4 and 21.6. So having done that, we know that the concentration in milliosmoles per liter is 300, because that's pretty much normal. That's what we're considering to be normal, milliosmoles per liter. And because because the osmolarity is the same in all the fluid compartments, we say that it's 300 in the intracellular fluid and 300 in the extracellular fluid as well. So that's 300 and 300. So now, how much in terms of milliosmoles do we have? This is milliosmoles per liter. This is liters. 300 times 36 is 10,800 milliosmoles. Okay? Of that, again, we have a 40-60 split. So 40% of the fluid is in the extracellular fluid. 14.4 times 300 is equal to 4320. I wasn't stupid, I did this in advance. And 21.6 times 300 is equal to 6480. Okay? So that's the first line. That's our initial condition. Okay? Now, this guy drank 2 liters of water. No electrolytes, nothing else in it, pure water. So the change from there will be 2 liters here, 2 liters of total body water consumed, all right? And that will be all extracellular volume, okay? We assume that the change is extracellular first, all right? We'll get to the redistribution of water between the compartments in a second, okay? So you should, of course, note that because it's pure water, you're not adding any milliosmoles at all. So that is a 0 and that is a 0, and you're not doing anything to the intracellular fluid at all, okay? So if we add 2 to 36, we get 38. We still have 10,800 milliosmoles after drinking all that water. The new osmolarity is 1080, which is the milliosmoles. And now we divide by our new total body water volume, which is 38, and that gives us 284. So our osmolarity dropped because we had a bunch of water in the system and nothing else. If we look at the extracellular fluid, 14.4 plus 2 is 16.4. We still have 4320 milliosmoles. And so 16.4, or 4320 divided by 16.4 gives you 263 milliosmoles per liter. And then the intracellular fluid is exactly the same. We haven't done anything to that yet. We added all of our volume to the intracellular space. So this is still 21.6. This is 6480, and this is 300. All right. So this is what we call the initial condition. All right. This is before water moves. Okay. So water has been drunk. It's been absorbed in the intestines. It's been added to the extracellular space. This is our condition. Now, before we get to our final condition, water has to move. All right? So how is water going to move in this case? Well, we know that in the end, you're going to end up with the same osmolarity inside the cells and outside the cells. In fact, you're going to end up with the same osmolarity everywhere in the body by the time that 2 liters of water is done redistributing. So, what that tells you is that this is the total body water, this is the osmolarity of the total body water. And I said during our lesson, this is going to be the same as these two. You can't have an osmolarity of total body water that's one value and then have individual compartments that are different values. They're going to all be the same value because they'll be the same osmolarity inside the cells and outside the cells. And if it's the same inside the cells and outside the cells, it has to be the same in the total body water because that's what the total body water is. So in the end, water is going to move until the osmolarity here and here is equal to the total body osmolarity. So in our final condition, we're going to still end up with 38 liters. We're going to still have 10,800 total milliosmoles, and we're still going to have 284 milliosmoles per liter. And now water is going to redistribute between the extracellular space and the intracellular space to make the osmolarity here the same as it is here. So the new osmolarity in the extracellular fluid will be 284. Okay? We have the same milliosmoles as we did before, 4320. And so we can calculate what the new volume is. This is milliosmoles per liter. This is milliosmoles. This divided by this gives you liters, and the new value will be 15.2. Okay? So that should make some sense to you. This osmolarity is lower than this, so water is going to move from the extracellular space to the intracellular space until they're equal at 284. So that's 15.2. How about the intracellular fluid? We started with 21.6 and 300, and our new osmolarity will be 284. The milliosmoles still 6480, and so 6480 divided by 284 gives you 22.8 liters. Okay, so our water is redistributed. So in terms of our change, we've added 2 liters to the total body water. That should make some sense. Of that 2 liters, 0.8 ended up in the extracellular space. That's 15.2 minus 14.4. Okay, and the rest of that, 1.2, ended up in the intracellular fluid. That is 22.8 minus 21.6. All right. So that's our final condition. Our final osmolarity, 284, dropped quite a bit. And of that, most of it ended up inside the cells, and you got a redistribution. Okay? All right. So that was the first problem. Now, having done that, let's do the second problem. Okay? So our second problem is very similar. Again, a normal man, 60 kilograms, average build. This time we're adding 1 liter of isotonic sodium chloride, IV. So this is something you'll do to a patient all the time, right? And we're going to do the same thing. We're going to figure out what the condition is before the IV, what the condition is after the IV. And we're going to assume he's normal before you do this, which means 300 milliosmoles per liter. Okay? So if we do that, we start, once again, it's the same weight, average build. 60% of the body weight is total body water, and again, that's 36, okay? And of that, 40% of that 36 is going to be extracellular, that's 14.4. And the rest is going to be intracellular, that's 21.6. Okay, those are the same numbers we started with in the last problem. Okay, we have again 10,800 milliosmoles because we have 300 milliosmoles per liter. Okay, 300 times 36 gives you 10,800. We have 300 milliosmoles per liter in the intracellular fluid. 300 times 14.4 gives you 4320. And we have 300 milliosmoles per liter in the intracellular fluid, and 300 times 21.6 gives you 6480. And again, those are identical numbers, so this was relatively easy. If you got the first problem, you got the beginning of the second problem. And this time, what we're doing is we're adding 1 liter total body water. And this time, it's not water, it's got particles in it. It's isotonic saline. Okay? Isotonic saline has 300 milliosmoles per liter. So if I add 300 milliosmoles per 1 liter of 300 milliosmoles per liter, I'm adding 300 milliosmoles to that, okay? Whoops, wrong spot. Let me get rid of that. Got rid of too much, sorry about that. 300, and this is 1, and that is 300 milliosmoles, okay? That's what we're doing to our total body water. Now, initially, when you add that, you're adding it all to the extracellular fluid. So the extracellular fluid, we will be adding 1 liter and 300, okay? And so when it's all said and done, we'll have 37 liters total body water. We'll have 1080 plus 300 milliosmoles. That is 100. And, 1110. Sorry about that. 10. Sorry. 11110. And there we go. 11110. Okay, and the total concentration will be 11110 divided by 37, and that is 300. So our osmolarity didn't change because we added an isoosmotic solution to the plasma, okay? So we added volume, we added the particles to go with it. In the end, we have more volume, more total body water, but the osmolarity didn't change because what we added was 300 milliosmoles per liter. Okay, on the outside of the cells, same thing, 15.4. We add 300 to our 4320, that makes 4620. And if you take 4620, divide by 15.4, lo and behold, you get 300, okay? And for the intracellular fluid, nothing has gone to the intracellular fluid yet, 21.6, 6480, and 300. It has not changed. So now, water will be distributed down an osmotic gradient. Well, here's the deal. There is no osmotic gradient. We're 300 on the outside, 300 on the inside, and that is equal to the 300 of the total body water. This is the condition that you want in your final condition. So it looks like nothing changes for the final condition because no water moves. So we have 37, 11, 110, 300, 15.4, and 4620, 300, 21.6, 6480, and 300. What's the final condition? We added 1 liter to the outside of the cells. We added 1 liter to the body, and all of it was extracellular fluid. Whoops. And all of it was extracellular fluid. So when you give an isotonic solution, isotonic saline, where all the particles are cell impermeant, to a patient, if it's isotonic and isoosmotic to the plasma, no water moves from the intracellular space to the extracellular space. All that ends up in the plasma. So this is a great way to expand your blood volume, for instance. If you've lost a lot of blood, you can give a bunch of isotonic saline, you can re-expand the blood volume up without changing the intracellular volume, which you oftentimes don't want to do. You don't want your cells shrinking and swelling. So this is the way that you do that, and this is why typically you give an isotonic, isoosmotic solution to patients, because a lot of times this is what you want to happen. All right? So these are typical problems. If you haven't done it already, do the fluids exercise. There's another problem like this in there, and there'll be a problem like this problems like this will crop up again. So be able to demonstrate that you understand what's going on when the osmolarity of the compartments change, and you understand what the consequences of that are in terms of what happens to the intracellular space and the extracellular space. That is, do the cells shrink or not? Or do they swell or not? Okay? All right. Thank you for your time. I'll see you guys in the rooms.